Picture this: a lone planet drifting through the infinite expanse of space. No star to orbit, no solar system to call home. This isn't a scene from a sci-fi novel. It's a cosmic reality known as a rogue planet. Imagine a world, perhaps as large as Jupiter or as small as Earth, traveling through the cosmic void, untethered and free. These wandering worlds, also known as orphan planets, challenge our understanding of planetary formation and the very nature of what we consider a planet to be. In the vast tapestry of our universe, these nomadic celestial bodies play a unique role. They are not bound by the gravitational embrace of a parent star, instead charting their own course through the galactic expanse. Their existence raises profound questions about the formation and evolution of planetary systems. As we embark on this cosmic journey, prepare to have your perceptions challenged. We'll delve into the mysteries surrounding these enigmatic worlds, exploring the theories behind their origins and the implications of their existence. Now, brace yourself for a mind-bending revelation. At this very moment, there could be billions of planets roaming through the interstellar space of our galaxy. Yes, you heard that right, billions. These aren't just barren rocks or gas giants. Some of these wandering worlds might have the potential for habitability. Imagine Earth-like planets floating in the cosmic darkness, carrying oceans, atmospheres, and possibly even the seeds of life, all without the warmth and light of a mother star. But here's where it gets even more intriguing. Orphan planets are far more than just astronomical curiosities. They are key pieces in the puzzle of understanding the chaotic dynamics of planetary formation and evolution. These cosmic nomads challenge our traditional views of how solar systems form and change over time. By studying these rogue worlds, we gain invaluable insights into the forces that shape our universe. They provide a unique laboratory for testing our theories about planetary physics, offering glimpses into extreme conditions we can't observe in traditional solar systems. As we unravel the mysteries of orphan planets, we're not just learning about distant, lonely worlds. We're piecing together the story of how planets form, how they interact, and ultimately, how they can be cast adrift into the cosmic ocean. This knowledge reshapes our understanding of our own solar system's history and stability. So, buckle up for a journey that will take you to the edge of our cosmic understanding. We're about to explore a universe where planets don't always play by the rules, where worlds can wander free, and where the possibilities for planetary existence are far more diverse than we ever imagined. If this cosmic journey through the mysteries of orphan planets has ignited your curiosity about the secrets of the universe, don't let your exploration end here. Hit that like button to fuel our cosmic voyage, and subscribe to Exploring the Universe to continue unraveling the wonders of space together. By joining our community, you'll be at the forefront of discovering what the cosmos has yet to reveal. From the depths of black holes to the birth of stars, and yes, the enigmatic orphan planets, we'll journey through it all. So, are you ready to expand your cosmic horizons? Like, subscribe, and let's embark on this incredible adventure across the universe. Orphan planets, also known as rogue planets, free-floating planets, or interstellar planets, are celestial bodies that orbit the galactic center directly, untethered to any star. These cosmic wanderers challenge our traditional understanding of planetary systems and offer intriguing insights into the dynamic nature of galactic evolution. Orphan planets are planetary mass objects that have been ejected from their parent star systems or have formed in isolation. Unlike the planets we're familiar with in our solar system, these bodies don't orbit a star. Instead, they drift freely through interstellar space, subjected only to the overall gravitational field of the galaxy. Key characteristics of orphan planets include planetary mass, typically between 0.1 and 13 Jupiter masses. Lack of nuclear fusion in their cores, distinguishing them from brown dwarfs. Direct orbit around the galactic center. Potential retention of moons or ring systems. The first confirmed detection of an orphan planet came in 2012 with the discovery of CUBSR 2149-0403, a Jupiter-sized object located about 100 light-years from Earth. This groundbreaking find opened up a new chapter in planetary science. Astronomers employ several methods to detect these elusive objects. This technique takes advantage of Einstein's theory of general relativity. When an orphan planet passes in front of a distant star, it briefly bends and magnifies the star's light, creating a detectable lensing effect. For younger, hotter orphan planets, advanced telescopes can sometimes directly capture their faint glow in infrared light. Large-scale surveys of the sky in infrared wavelengths can potentially reveal cooler orphan planets. Precise measurements of star positions over time might reveal the gravitational influence of nearby, unseen orphan planets. The prevalence of orphan planets in our galaxy has been a subject of intense scientific debate and research. Current estimates suggest that orphan planets could be astonishingly common. Some studies propose that there might be up to 2 orphan planets for every star in the Milky Way. With an estimated 100 to 400 billion stars in our galaxy, this could mean 200 to 800 billion orphan planets. More conservative estimates still suggest billions of these wandering worlds in our galaxy alone. Microlensing surveys indicate that low-mass free-floating planets are more common than Jupiter-mass objects, suggesting a vast population of Earth-sized orphan planets. These staggering numbers have profound implications for our understanding of planetary formation and galactic evolution. They suggest that the ejection of planets from young star systems might be a common occurrence, reshaping our views on the stability and development of planetary systems. The abundance of orphan planets also raises intriguing questions about the potential for life in the universe. While these worlds lack the warming light of a star, some scientists speculate that larger orphan planets might retain enough internal heat to support subsurface oceans and potentially simple forms of life. As our detection methods improve and new space telescopes come online, we expect to refine these estimates and perhaps even directly image some of these cosmic wanderers. The study of orphan planets is still in its infancy, promising exciting discoveries that will continue to reshape our understanding of the cosmic landscape. The ejection of planets from their host systems is a fascinating and complex process that highlights the dynamic nature of planetary systems. This theory suggests that orphan planets were once part of a star system but were violently expelled due to various astronomical events. Planetary ejection occurs when a planet gains enough kinetic energy to overcome the gravitational binding energy of its host star. This process typically happens during the early, chaotic stages of planetary system formation or during later disruptive events. Once ejected, the planet becomes a free-floating object in interstellar space. In multi-planet systems, planets can engage in a gravitational dance that can become unstable over time. Larger planets, particularly gas giants, can significantly perturb the orbits of smaller planets. These interactions can lead to orbital resonances, which may amplify over time and result in ejection. In some cases, a gravitational slingshot effect can occur, where one planet gains momentum at the expense of another, potentially leading to ejection. Stars in dense stellar neighborhoods or clusters can pass close to each other. Such close encounters can severely disrupt planetary orbits. The gravitational influence of a passing star can directly eject planets or induce instabilities that lead to later ejections. This scenario is more common in the dense core of globular clusters or in the galactic center. When massive stars end their lives in supernova explosions, the sudden loss of mass can dramatically alter the gravitational landscape. Planets that survive the initial blast may find themselves unbound from the remnant star. Even in less extreme cases, such as the evolution of lower-mass stars into white dwarfs, the loss of stellar mass can destabilize planetary orbits. Numerous computer simulations have been conducted to model the dynamics of planetary systems, providing strong support for the ejection theory. N-body simulations of early solar system formation show that ejections are common during the chaotic early stages of planetary evolution. Models of the solar system's history suggest that our system may have once contained additional gas giants that were ejected. Simulations of planetary systems around binary stars indicate a higher rate of planetary ejections due to complex gravitational interactions. Recent high-resolution simulations have shown that even in stable systems, long-term evolution over billions of years can lead to ejections. These simulations not only support the plausibility of planetary ejections, but also help explain the observed diversity of exoplanetary systems and the potential abundance of orphan planets. While ejection from host systems is a compelling theory, some scientists propose that orphan planets might form in isolation, without ever being part of a star system. This theory challenges our traditional understanding of planetary formation. The isolated formation theory suggests that some planetary mass objects could form directly from the collapse of small pockets within giant molecular clouds, similar to how stars form, but on a smaller scale. Key points of this theory include fragmentation of large molecular clouds into smaller, substellar mass clumps. These clumps would need to be dense enough to collapse under their own gravity, but not massive enough to initiate hydrogen fusion. The process would be similar to star formation but halted at an earlier stage due to insufficient mass. The concept of subnebulae refers to small, localized regions within larger molecular clouds that could potentially collapse to form planetary mass objects. These subnebulae would need to be sufficiently isolated from nearby forming stars to avoid being incorporated into their protoplanetary disks. The collapse process would likely involve the formation of a small circumplanetary disk, potentially leading to the formation of moon systems around the orphan planet. This process might be more common in low-density regions of molecular clouds, where stellar formation is less prevalent. While direct evidence for isolated planet formation remains elusive, several observations lend credence to this theory. Objects with masses just above the planetary threshold have been observed, suggesting a continuum of formation processes from stars down to planets. Some objects with planetary masses have been found in young star clusters, without clear evidence of having been ejected from a specific system. These have revealed small, dense cores that could potentially be sites of isolated planet formation. This suggests these objects formed through a process similar to star formation, rather than within a larger protoplanetary disk. Some studies suggest a continuous distribution from low-mass stars through brown dwarfs to planetary mass objects, hinting at a shared formation mechanism. While both the ejection and isolated formation theories have merit, the reality is likely a combination of both processes contributing to the population of orphan planets. Ongoing research and future observations will help refine our understanding of these enigmatic cosmic wanderers. Binary and multiple star systems play a crucial role in the formation and ejection of orphan planets. These complex stellar environments create dynamic, often chaotic conditions that can significantly impact planetary formation, stability, and ultimately, ejection. In multi-star systems, planets are subjected to the gravitational influence of multiple massive bodies. This creates a complex gravitational field that can lead to highly irregular and unpredictable planetary orbits. The stability of planetary orbits in these systems is often tenuous, with small perturbations potentially leading to drastic orbital changes. Multiple stars can create various orbital resonances that affect planetary motion. These resonances can either stabilize or destabilize planetary orbits, depending on the specific configuration. Over time, destabilizing resonances can amplify, leading to planetary ejection. The presence of multiple stars can disrupt the protoplanetary disks where planets form. This disruption can lead to irregular planet formation or create conditions favorable for planetary ejection early in the system's history. As stars and multiple systems evolve, their changing masses and sizes can alter the gravitational dynamics of the entire system. This evolution can destabilize previously stable planetary orbits, potentially leading to ejections. The slingshot effect, also known as a gravity assist, is a phenomenon where a planet's orbit is dramatically altered by a close encounter with a massive body, in this case, a star in a binary system. Key aspects of the slingshot effect include: a planet in a wide orbit around a binary pair can have close encounters with one of the stars during its orbit. During these encounters, the planet can gain or lose orbital energy and momentum. If the planet gains enough energy, it can be ejected from the system entirely. This effect is particularly powerful in binary systems with stars of unequal masses or in eccentric orbits. The slingshot effect can also occur in single-star systems during planetary encounters, but it's especially prevalent and powerful in binary systems due to the additional gravitational influence. Recent research has provided valuable insights into the frequency and nature of planetary ejections in various stellar systems. Studies suggest that binary star systems are more likely to eject planets than single-star systems. Some models indicate that the ejection rate in binary systems could be up to 3 to 4 times higher than in single-star systems. Research shows that wide binary systems, with separations greater than 1,000 Australian dollars, are more likely to retain planets in stable orbits. Closed binary systems tend to have higher rates of planetary ejection due to stronger gravitational interactions. Higher mass stars and systems containing at least one massive star show increased rates of planetary ejection. Systems with evolved stars, e.g., white dwarfs or neutron stars, can experience late-stage planetary ejections due to mass loss and gravitational dynamics changes. Systems with multiple giant planets show higher ejection rates, particularly during the early stages of system formation. The presence of a Jupiter-like planet in a system can significantly increase the likelihood of smaller planets being ejected. While many ejections occur early in a system's history, recent studies suggest that ejections can continue to occur over billions of years. Long-term simulations have shown that even seemingly stable systems can experience late ejections due to subtle, long-term gravitational interactions. These studies not only help us understand the origin of orphan planets, but also provide crucial insights into the long-term stability and evolution of planetary systems in various stellar environments. Is the idea of lonely worlds wandering through the cosmos making your mind drift into the stars? If so, don't forget to hit that like button. Your engagement helps us continue exploring these cosmic mysteries with you. Plus, it lets us know you're as excited about these celestial nomads as we are. So, if you're ready for more mind-bending space science, smash that like button and let's keep this cosmic journey going. Orphan Planets, drifting alone in the vast expanse of interstellar space, possess unique characteristics that set them apart from their star-bound counterparts. Understanding these characteristics is crucial for unraveling the mysteries of their formation, evolution, and potential for harboring life. The composition of orphan planets is expected to vary widely, reflecting the diversity of their origins and the circumstances of their formation or ejection. Many orphan planets are thought to be gas giants, similar to Jupiter or Neptune. These planets likely formed in the outer regions of their original star systems, where they could accumulate large amounts of hydrogen and helium. Their substantial size and mass would have made them more resistant to complete disintegration during the ejection process. Examples might include planets with masses ranging from that of Neptune to several times that of Jupiter. Smaller, rocky orphan planets are also possible, though they may be less common or harder to detect. These could be similar in composition to terrestrial planets like Earth, Mars, or even smaller bodies like large moons or dwarf planets. Rocky orphans might have originated in the inner regions of their star systems, or could be the cores of gas giants that lost their atmospheres during violent ejection events. Some orphan planets might have compositions that don't neatly fit into the gas giant or rocky planet categories. These could include super-Earths with thick atmospheres, or mini-Neptunes with substantial rocky/icy cores and less extensive gaseous envelopes. The ratio of gaseous to rocky orphan planets is still a matter of ongoing research, with detection biases favoring the discovery of larger, gaseous bodies. One of the most intriguing aspects of orphan planets is their ability, or inability, to retain atmospheres without the constant input of energy from a host star. Planetary mass. More massive planets have stronger gravity, making it easier to hold onto their atmospheres. Heavier molecules are less likely to escape than lighter ones. Colder atmospheres have lower particle velocities, reducing escape rates. Magnetic field. A strong magnetic field can help protect the atmosphere from erosion by stellar winds and cosmic rays. Large gas giants are expected to retain most of their original atmospheres. Their substantial gravity and the extreme cold of interstellar space would significantly slow atmospheric loss. The atmospheres of these planets would gradually cool and contract over time. Smaller, rocky orphan planets face greater challenges in retaining atmospheres. Without the constant energy input from a star, these atmospheres would likely freeze onto the planet's surface, creating a thin layer of exotic ices. Any residual atmosphere might consist of trace amounts of outgassed materials from the planet's interior. The unique conditions of orphan planets might lead to atmospheric compositions unlike anything seen in starbound planets. Extremely low temperatures could result in atmospheres with unusual chemical equilibria. While orphan planets lack the external heat source of a star, internal heat generation can play a crucial role in their evolution and potential habitability. Long-lived radioactive isotopes in a planet's interior can provide a steady, albeit diminishing, heat source over billions of years. Orphan planets that retain large moons could experience significant tidal heating, similar to Jupiter's moon Io. Larger planets, especially, can retain significant heat from their initial formation for billions of years. Gas giants can generate heat through gravitational contraction over long periods. Internal heat in gas giants could drive atmospheric circulation and weather patterns. This heat might maintain a liquid metallic hydrogen layer, potentially generating a magnetic field. Internal heat could maintain a molten core, driving tectonic activity and volcanism. This could lead to the cycling of materials between the interior and surface, potentially creating conditions favorable for simple forms of life. In some cases, internal heat could maintain liquid water oceans beneath thick ice shells. This scenario is particularly intriguing for the potential habitability of orphan planets. Over time, internal heat sources will diminish, leading to gradual cooling and solidification. The timescale for this cooling depends heavily on the planet's size and composition. Understanding these characteristics not only helps us comprehend the nature of orphan planets, but also expands our understanding of planetary evolution in extreme conditions. As our detection and observation capabilities improve, we may discover orphan planets with unexpected properties, further enriching our knowledge of these cosmic wanderers. The discovery and study of orphan planets present unique challenges due to their faint nature and lack of a host star. Scientists have developed and refined several methods to detect these elusive cosmic wanderers, each with its own strengths and limitations. Gravitational microlensing has emerged as one of the most powerful tools for detecting orphan planets, especially those of lower mass. How it works? Based on Einstein's theory of general relativity, massive objects can bend light from a background source. When an orphan planet passes in front of a distant star, it acts as a gravitational lens, temporarily magnifying the star's light. Astronomers observe the characteristic brightening and dimming of the background star over time, creating a unique light curve. The shape and duration of this light curve can reveal information about the lensing object's mass, allowing scientists to identify planetary mass bodies. Why it's crucial: sensitivity to low-mass objects. Microlensing can detect planets as small as Mars, making it uniquely suited for finding smaller orphan planets. This method can detect planets at great distances, even in other galaxies. No need for light from the planet. Since we're observing the lensed star's light, the planet itself doesn't need to emit or reflect light to be detected. Statistical power. While individual events are not repeatable, large-scale surveys can provide statistical data on orphan planet populations. Challenges. Each microlensing event happens only once, making follow-up observations challenging. Light curves can be complex, requiring sophisticated models to interpret accurately. Direct detection involves capturing actual light emitted or reflected by the orphan planet itself. While extremely challenging, this method offers the potential for detailed characterization of these objects. Challenges. Without a star's reflected light, orphan planets are incredibly dim. Most orphan planets are expected to be very cool, emitting primarily in infrared wavelengths. Searching for point-like objects across vast areas of sky is time-consuming and computationally intensive. Current and future possibilities. Large-scale infrared sky surveys can potentially reveal warmer, younger orphan planets. Advanced adaptive optic systems on large ground-based telescopes can help overcome atmospheric distortions. Future extremely large telescopes may be able to directly image cooler and smaller orphan planets. Researchers are exploring methods like polarimetry to distinguish planetary light from background noise. Potential breakthroughs. Direct detection could allow for spectroscopic studies of orphan planet atmospheres. Observing changes over time could reveal information about rotation, weather patterns, and even potential moons. Space-based telescopes, free from atmospheric interference, play a crucial role in the hunt for orphan planets. The James Webb Space Telescope and other future missions are set to revolutionize this field. JWST's large mirror and advanced instruments provide unparalleled sensitivity in the infrared spectrum. Its ability to survey large areas of sky efficiently can help in identifying candidate orphan planets. JWST can perform detailed spectroscopic analysis of detected objects, potentially revealing atmospheric composition. JWST can provide follow-up observations for candidates identified by other methods like microlensing. While designed for exoplanet imaging around stars, this technique might be adapted for very bright orphan planets, particularly suited for detecting cool, low-mass objects like brown dwarfs and massive orphan planets. Set to conduct large-scale microlensing surveys, potentially discovering thousands of orphan planets. These proposed missions could have the capability to directly image smaller, Earth-like orphan planets. Space telescopes like JWST can work in tandem with ground-based facilities, each complementing the other's strengths. For example, ground-based telescopes might identify candidates that JWST can then characterize in detail. Telescope time on JWST is in high demand across many fields of astronomy. Space telescopes have finite operational lifespans, necessitating careful prioritization of targets. The combination of these detection methods, particularly the synergy between ground-based microlensing surveys and space-based direct imaging and spectroscopy, promises to greatly expand our understanding of orphan planets in the coming years. As technology advances, we may uncover a vast population of these wandering worlds, potentially revolutionizing our understanding of planetary formation and galactic ecology. The concept of habitability for orphan planets challenges our traditional understanding of life-supporting environments. These starless worlds, drifting through the cosmic void, present unique conditions that could potentially harbor life forms vastly different from those we're familiar with on Earth. Without the constant energy input from a host star, orphan planets must rely on alternative sources to generate and maintain conditions potentially suitable for life. Long-lived radioactive isotopes in the planet's interior can provide a steady, albeit gradually diminishing, heat source. Elements like uranium, thorium, and potassium-40 continue to decay over billions of years, warming the planet from within. This heat can drive geological processes and potentially maintain liquid water beneath the surface. Orphan planets that retain large moons can experience significant tidal forces. The gravitational interaction between the planet and its moons can generate frictional heating within the planet's interior. This mechanism is observed in our solar system, most notably in Jupiter's moon Io and Saturn's moon Enceladus. Larger planets, particularly gas giants, can retain a significant amount of heat from their initial formation. This primordial heat can persist for billions of years, slowly radiating outward from the core. Gas giant planets can generate heat through ongoing gravitational contraction. As the planet slowly contracts under its own gravity, it converts gravitational potential energy into thermal energy. Certain chemical reactions within the planet could serve as localized energy sources. For example, serpentinization reactions between water and olivine-rich rocks can produce hydrogen, a potential energy source for chemosynthetic life. High-energy particles from cosmic rays could potentially drive chemical reactions on the planet's surface or in its upper atmosphere. While not a significant heat source, this could provide energy for simple chemical processes. One of the most intriguing possibilities for habitability in orphan planets is the potential existence of subsurface oceans, particularly in larger, Jupiter-like worlds. Internal heat sources, particularly radiogenic and residual heat, could maintain temperatures sufficient for liquid water beneath a thick ice shell. High pressure from the overlying ice and atmosphere could keep water liquid even at temperatures below 0 degrees Celsius. These oceans might contain a mixture of water and other compounds, such as ammonia or methanol, acting as antifreeze. The specific composition would depend on the planet's formation history and subsequent evolution. Interactions between the rocky core and the ocean could lead to a rich variety of dissolved minerals and organic compounds. Hydrothermal vents, similar to those found in Earth's oceans, could provide localized hotspots of chemical activity. Subsurface oceans in large orphan planets could potentially remain stable for billions of years, providing long-term environments for potential life to evolve. While challenging to detect, future advancements in technology might allow us to infer the presence of these oceans through careful observation of the planet's magnetic field or subtle changes in its shape due to tides. The unique conditions on orphan planets could potentially give rise to life forms vastly different from those found on Earth. While highly speculative, considering these possibilities helps broaden our understanding of potential life in the universe. In the absence of sunlight, life could evolve to harness chemical energy sources. Organisms might use hydrogen, methane, or other chemicals as energy sources, similar to some extremophiles found near Earth's hydrothermal vents. Organisms in subsurface oceans would need to withstand enormous pressures. They might evolve unique cellular structures or biochemistries to thrive in these high-pressure environments. Life in the upper layers of subsurface oceans or in the ice shell might evolve to function at temperatures near or below 0 degrees Celsius. This could involve unique enzymes or cellular membranes adapted for extreme cold. For any life on or near the surface, resistance to cosmic radiation would be crucial. This might lead to the evolution of highly efficient DNA repair mechanisms or alternative information storage molecules. The unique chemical environments of orphan planets could potentially support life based on different biochemistries. Speculation includes the possibility of silicon-based life or organisms using liquid methane or ammonia as a solvent instead of water. In resource-scarce environments, life might evolve as collective entities rather than discrete individuals. This could manifest as large, diffuse networks of simple organisms working in concert. Given the limited energy sources, life might evolve extremely slow metabolisms. Organisms could have lifespans and reproductive cycles spanning thousands or even millions of years. In perpetually dark subsurface oceans, life might evolve bioluminescence for communication or predation. While these speculations are based on our current understanding of biology and planetary science, it's important to note that life, if it exists on orphan planets, could be so alien that it defies our current categories and expectations. The study of these wandering worlds not only expands our search for extraterrestrial life, but also challenges us to reimagine the very definitions of life and habitability. The potential for habitable conditions on orphan planets underscores the importance of expanding our search for life beyond traditional star-centered planetary systems. As our detection and analysis capabilities improve, these lonely wanderers may prove to be some of the most intriguing targets in our quest to understand life's potential in the universe. As our understanding of the universe expands, the study of orphan planets stands at the forefront of astronomical research, promising to revolutionize our comprehension of planetary formation, galactic dynamics, and potentially, the prevalence of life in the cosmos. The future of this field is bright, with numerous planned missions, emerging technologies, and paradigm-shifting potential discoveries on the horizon. The coming decades will see a surge in capabilities for detecting and studying orphan planets, driven by both ground-based and space-based initiatives. Space-based missions. Nancy Grace Roman Space Telescope. Scheduled launch. Mid-2020s. Wide-field imaging and spectroscopy. Microlensing surveys. Expected to discover thousands of orphan planets, providing a statistical understanding of their prevalence. LUVOIR. Potential launch. 2030s. Extremely sensitive direct imaging and spectroscopy. Could potentially directly image and characterize smaller, Earth-sized orphan planets. HabEx. Alternative to LUVOIR, focusing on direct imaging of exoplanets. Could provide detailed atmospheric analysis of detected orphan planets. Ground-based observatories. Extremely large telescope. First light expected, mid-2020s. Unprecedented light-gathering power. Advanced adaptive optics. Potential for direct imaging of larger orphan planets and detailed spectroscopic analysis. 30-meter telescope and Giant Magellan Telescope. First light expected, late 2020s. Will complement ELT in the Northern Hemisphere, providing all-sky coverage. Advanced adaptive optics. Next-generation systems to further mitigate atmospheric distortion. Could dramatically improve ground-based direct imaging capabilities. Starshade technology, while designed for exoplanet imaging around stars, could be adapted for very bright orphan planets. Potential for future space-based missions. Machine learning and AI. Enhanced data processing algorithms to identify orphan planet candidates in large datasets. Improved modeling of planetary atmospheres and interiors. Improved infrared detectors. More sensitive detectors for capturing faint infrared emissions from cool orphan planets. The investigation of orphan planets has the potential to dramatically reshape our theories of planetary formation and evolution. Studying the population of orphan planets can help determine the relative importance of different formation processes. Core accretion versus gravitational instability. May reveal previously unknown formation pathways specific to orphan planets. The abundance and characteristics of orphan planets can inform models of planetary migration and ejection. Could provide insights into the stability and evolution of multi-planet systems. Comparing orphan planets to their star-bound counterparts may reveal the influence of host stars on planetary evolution. Could challenge assumptions about the necessity of stars for planet formation. Understanding the distribution of orphan planets throughout the galaxy may inform theories of galactic evolution. Could reveal connections between orphan planet populations and galactic structures, e.g., star-forming regions, galactic bulge. Discovering very low-mass orphan planets could redefine the boundary between planets and substellar objects. Studying atmospheres of orphan planets can provide insights into atmospheric evolution without stellar influences. Observations of orphan planets can test and refine models of planetary interiors under various conditions. The quest to find orphan planets close to our solar system is a particularly exciting aspect of future research, offering the potential for more detailed studies. Closer objects allow for more detailed observations and potentially direct exploration in the distant future. Could provide insights into the history of our own solar system. Infrared sky surveys. Continuing and expanding all-sky surveys to detect faint, cool objects. Missions like NEO-CAM could serendipitously detect nearby orphan planets. Astrometric measurements. Precise position and motion measurements can reveal the gravitational effects of unseen objects. ESA's Gaia mission and its potential successors could detect nearby orphan planets through their gravitational influence. Citizen science projects. Involving the public in the search through projects like Backyard Worlds, Planet 9. Potential discoveries. Objects between the mass of Jupiter and the smallest brown dwarfs. Ejected solar system objects. Planets or planetesimals that may have been ejected from our early solar system. Captured interstellar objects. Orphan planets that may have been gravitationally captured by our solar system. A nearby orphan planet would provide an unprecedented opportunity for detailed study. Could potentially reveal the presence of moons or ring systems around orphan planets. Might inform debates about the existence of a hypothetical Planet 9 in our outer solar system. Extremely faint nature of these objects makes detection difficult, distinguishing between distant Kuiper belt objects and true orphan planets. Development of interstellar probe concepts that could potentially visit nearby orphan planets in the distant future. Continuous monitoring could reveal long-term changes in these objects, informing models of their evolution. The future of orphan planet research is poised to open new frontiers in our understanding of the universe. As we develop more advanced technologies and methods, we may find that these solitary wonders are far more common and diverse than previously imagined. Their study not only enriches our knowledge of planetary science but also challenges us to reconsider fundamental questions about the nature of planets, the prevalence of life, and our place in the cosmic tapestry. The coming decades promise exciting discoveries that may well rewrite our understanding of the universe and our place within it. The study of orphan planets has opened up a new frontier in our understanding of the cosmos, challenging our preconceptions and expanding our horizons in ways we could scarcely have imagined just a few decades ago. As we conclude our exploration of these enigmatic wanderers, it's essential to reflect on the profound implications of their existence and the exciting future that lies ahead in this field of research. If this journey through the mysteries of orphan planets has ignited your curiosity about the secrets of the cosmos, don't stop here. Subscribe to the Exploring the Universe channel to continue unraveling the wonders of the universe. Together, we'll delve into the most intriguing enigmas of space and discover what the cosmos still has in store for us. By subscribing, you'll join a community of fellow cosmic explorers, gaining access to regular updates on the latest discoveries in orphan planet research, in-depth explorations of other fascinating astronomical phenomena, stunning visualizations that bring the wonders of the universe to life. Don't miss out on the next big revelation about our vast and mysterious universe. Hit that subscribe button now, and let's embark on an epic journey of cosmic discovery together. The universe is waiting to be explored. Are you ready to join the adventure?